Hi guys, welcome back. We're currently in the middle of a very important section that will at the end of the day spit out many big theorems in functional analysis. The section began with a statement about certain sets having non-empty interiors and that allowing us to conclude that linear maps are bounded, aka continuous. After that, we quickly reviewed the contour intersection theorem about certain nested closed sets in a complete metric space, and if they shrink down in diameter, then the intersection is going to contain precisely one point. This was a warm-up in some sense for the bare category theorem about being again in a complete metric space and having a countable intersection of open dense subsets. That intersection, then that's the statement of the theorem, is again going to be dense. We then, after having proven that theorem, we then rephrased it as a corollary about unions of closed subsets in a complete metric space. If that union is going to be it's a countable union, that's important. If that countable union of closed subsets in a complete metric space is the whole space, then at least one of them has to have a non-empty interior. Now, having established this fact, we are now gonna use it again in a second application. The first application that we did last time was the principle of uniform boundedness. This is one of the very big theorems in functional analysis. We have family of bounded linear transformations between two Banach spaces, and that family is pointwise bounded. I explained precisely what this means, then it's actually uniformly bounded. This is a remarkable statement. The second remarkable statement that will come out of bare category is displayed here on top of the slide. This is the open mapping theorem. So if you have a bounded linear transformation T between two Banach spaces, a transformation that is surjective, equivalently onto, then it is an open map. That is to say, it maps open sets in X to open sets in Y. All right. I gave some context about this. I said there's other open mapping theorems. There's one in complex analysis about non-constant analytic functions, also doing just that, mapping open things to open things. And I explained why maybe this is remarkable, because, for instance, here in green, the example is still there. So you have sine, which the way it is written here is surjective. The real number with the absolute value is a Banach space. Now, of course, that -1 is not, because it's not even a vector space. So you shouldn't expect, stuff to work out, that this is an open map. And it's not. It maps the real line, which is open, to something closed, right? So, but besides that, the target is not the Banach space. Also, this function is clearly nonlinear, right? So that just doesn't work out. All right, now what we will do is we will prove this theorem, and then once done, we will build up to the next big result in this section. All right, so we will use, open maps, it's good to start with open balls. So there will be two kinds of open balls. There will be the open balls in the X space, in the domain space, so to speak. They will get this superscript X, and likewise the ones in the target space will get a superscript, Y, say. Okay, we will use open balls BRX and X in X and Y. Just a notation, all right? And proof, what are we going to prove up front? That for some are positive, this one here, we're going to start just with the simple ball of radius R centered at 0 in X space, and it's going to be mapped to something in Y space, and we're going to show this has a non-empty interior. And then once this is established, then we'll be almost done. So remember, an interior of a set in a metric space is the largest open ball that you can, fit in it. Right? So to this end, begin with, now we want to use bare category, more precisely that corollary to it. So we're going to start with something closed. Hopefully the union of that closed stuff is going to, give us everything. And then we have to see where we can go from there. So first off, define these guys. So look at the image of a ball of radius n being a natural number, and stick it into T. Now what comes out in general is not going to be closed. That's why I take, I join all limit points to it, and that's why I take the topological closure there. So that's now a closed set. Because closures are closed, right? Each Cn is closed. And since, well, so if you look at Tbnx at 0, right? So remember, T is surjective. That's now crucial. So every point is hit by something under the map T, right? And of course, that point, at some point, it will lie in a disk of sufficiently large radius. So what I can say is, if I take the union of all those images of those disks with increasing radius, surely because T is surjective, I'm going to hit everything eventually, right? So I have certainly this, and hence you can take the topological closure of both sides. The right-hand side won't change, and the left-hand side will precisely give you the union of the Cn's. So we have n1 infinity Cn is equal to y. Okay, so there you have it. So that prepares, and here we clearly use surjectivity precisely at this inequality, right? Because everything in the y space is hit by something under the map T, and well, that you can then trace back to lying in some ball of sufficiently large radius, and then if you take the union of all those things, you will get everything. All right. So now you have this, and now this, of course, prepares very much bare category theorem. Thus, by the corollary to the bare category theorem, some of those, at least one of them, that's more accurate, has a non-empty interior. So some Cn0 has non-empty interior, and that means you can squeeze an open ball in it, right? Has non-empty interior. That is for some and not some y0 in y and and radius rho positive, we have that, well, this ball, I can't say much about its center or anything, so I have to be fairly general, but it's going to be sitting in this Cn0, which is by definition T, Bn not x 0, and then the closure thereof, right? That's precisely what it means for something to have a non-empty interior. You can squeeze an open ball in it. You don't know the radius, you don't know the center, but nevertheless a ball. All right, good. So now, the thing is now, if we were able, by some reasoning, to get rid of this closure up here, right, then we would be almost done, right? Because then you have an open ball, this Bn0x, and under T, you would have proven that there is an open ball in it. So it would be an open mapping indeed. But currently we're not there yet because this is something closed, right? So now how do we assure that we can squeeze an open ball in that closed thing there, right? So, all right, so there's some argument that needs to be done. So we now need to show that some TBRX0 has non-empty, so without the closure, that's the important thing, has non-empty interior. And that will heavily rely on the linearity of the map. So far, as you might have noticed, we haven't exploited the linearity whatsoever. All right. So I need a yellow star, by this equation here. So what does this equation mean here? So this closure there, right? Set of all limit points. So it means simply that whenever you have an element here in the left-hand side, then you can get arbitrarily close to it by something in the right-hand side, right? And something in the right-hand side is the image of something in this ball, right? That's precisely what this set containment means here. Now we're gonna, what I just said in words, we're now gonna write down in two formulas. So first off, by by star given an arbitrary point y in, well, as I said, so you can pick a point in that ball on the left. What I'm gonna do here is slightly different. I'm gonna pick a point in the left, but the center equal to 0, so that I have to translate it around. So we can find a sequence xm, m1 infinity, 0, b, n0, x, 0, so that, well, the image of it creeps up to xm y0 plus y. Okay, so in a sense, this one, because here's the origin, so what you do is, well, you go a little bit away from the center. Why not, right? Because by this yellow star, certainly the center you can creep up to by something in the right hand side. And now you go, well, at most distance rho away. That's precisely what's written up there from the center, and then you can still creep up to it. So that's why I said it's an easy translation. As m goes to infinity, right? Additionally, by star again, we can find a sequence, say, Zm, m1 infinity in bn0 x 0, so that tzm goes to the center, right? So that second one, that probably requires no explanation, because the ball on the left, its center is y0, so that all that I'm saying right now is you can take something in the right and creep up to the center y0, and that's certainly true because of the topological closure. All right, but now what you do is you take a combination of these two sequences, txm minus zm, and now you use for the first time the linearity, right? This is txm minus tzm, and excuse me, those together, they creep up to what? The first one to y0 plus y, the second one to y0, so you subtract it off, then you creep up to y, right, as m goes to infinity. Okay, well, what does this mean? Proving that since y was an arbitrary point in this ball, okay, proving that this ball with the center 0 is contained in where? Well, t, b, x, 0, closure thereof, because we just approximated here by a sequence. We hit it by a limit of this image sequence. But now what about the radius of the ball? Well, this first element is, where is it? In a ball of radius n0, and so is the second one, right? That means that linear combination is at worst in a ball of twice the radius, right? 2n0. So that's why I have here 2n0. Okay, so this little trickery, what it allowed me to do is, if you compare with the yellow equation earlier, with the yellow star, it allowed me to translate my center towards the origin and still prove that, well, that ball at the origin is in this guy here on the right, but perhaps with twice the radius. Okay, that's what I achieved right now. All right, that's the first step. Now the second step, that is more to do with the linearity. So since t is linear, if you take a ball of radius lambda times alpha at 0, that's why you want to put it at 0, otherwise the argument is not quite true, because otherwise you would also have to scale the center. But here, if the center is 0, you can just pull out the lambda from the ball, right? And that is the linearity. Oh, I forgot the t. T b alpha x 0, right? This is bilinearity for any lambda alpha positive bilinearity of t. We conclude that this one, double star, yields, so what you can do is you just rescale, so there is existence of epsilon positive, so that you just divide this little radius here, 2n0 by, well, n0 by 4, you divide it by 4 times n0, and then the ball on the left hand side would be rescaled accordingly, and that result you call epsilon. That resulting radius you call epsilon. Is sitting in t b 1/2 x 0, like this. Okay, so that's the only thing that we achieved so far. All right, hence then exploiting the scaling invariance furthermore, by the scaling invariance. By this I mean this little equation here, the green one, which is linearity after all. You can do this much better for each n integer, non-negative. You can do epsilon divided by 2 to the n in y space, sitting in b 1/2 n plus 1 x 0, right? The equation on top was just n equals to 0, but you can do this with higher powers of n, all right? So now this will be equation triple star, and now we will use this equation. We now use triple star to prove that b epsilon y 0 is contained in t b1 x 0. Okay, so how to do this? Well, it's a set inclusion, so take an arbitrary point in the left and show that it, well, is in the right. Okay, so take a point in the left, y, and now pick sequence of points x0, x1 inductively, so that the xj is in a ball of shrinking radius, namely 1/2 to the j plus 1, centered at 0, and, well, the distance from that point y under the map T, some of those elements is also getting small, epsilon to the 2 j plus 1. Okay, how is this possible? How can I choose this sequence? Well, indeed, we can first pick x0 in the ball with radius 1/2 in x space, with y minus t x0 less than epsilon over 2. Why is this? Well, because of, well, we could say triple star. I'll quickly go back to that. Because of triple star, because in triple star, when you take n equals to, let's say 0, right? And if you take a, is that 0 that I want? Yeah, that's right. Yeah, it's n equals to 0, right? And you have on the left this y element, which is sitting in here, right? And you have your x in there. And since that ball of radius at most epsilon over 2 is sitting inside the closure of that image, the distance between y and your first element x0, which is in here, cannot exceed that epsilon over 2, right? So that is certainly true. Good. And now once you have the first step, then you iterate the procedure, right? So this is sort of the base step, and then xj inductively, since what? Y minus tx0 plus xj minus 1 is in b epsilon 2j in y space 0. And then once you have this distance, then you choose the next one, x sub j, and use the same equality again. The only difference being now that the power 2 is no longer, that the denominator 2 in epsilon over 2 is no longer raised to the power 1, but to the power j, or then j plus first, right? So that's the difference, okay? Since this, and since we have the yellow triple star. All right, so that works. All right, in this way, what do you get? In this way, you create a sequence of partial sums, xj, all the way up to n, and n is the running index, n1 to infinity. That's the sequence of points in x, which is Cauchy. Right, this is simply because how those xj's are chosen, because the norm of xj is at most 1 over 2 to the j plus 1, and that is a geometric. If you substitute it into that sum down here, that's going to be a geometric sum. So as n goes to infinity, that's going to be certainly be a Cauchy sequence, right? It's Cauchy, since x is a Banach space, it is convergent, so has a limit j1n xj goes to x, say as n tends to infinity. And this x, well, okay, I have to write where the x is contained in. X is in the first one, in b1 x0, okay, as n tends to infinity. And moreover, and now you use the continuity finally, aka the boundedness of t, because t is a continuous map, so you can take the limit inside. For instance, you can let n go to infinity in this equation. On the right hand side, since you have a sum, then on the right hand side you will shrink to 0. This sum here, that will go to your x, and then y minus tx will be equal to 0 in the norm, so y is equal to t of x. That's precisely what I wrote there. All right, so we have this. Now this proves that we started with y in the ball b epsilon of radius epsilon in y space, and now I realize it as t of x, where x is in bx0. So this proves simply, and since y was arbitrary, this proves simply b epsilon y0 is contained in t b1 x0, and no longer any closures there. Okay, with this in hand, we now complete the proof. Right, so how to do this? Let u in x space be open and y in the image of that open set, meaning there is x in u with tx equals to y, right? Now, since u is open, we can find positive delta, so we can squeeze a ball with center x in it. But by what we just proved, b epsilon y, 0 being contained in t b1 x0, and the aforementioned scaling invariance, we actually have, well, we can scale the ball by an additional delta, so b epsilon delta on the left instead of b epsilon. That thing will then be in b delta x0, the image thereof, which implies which implies, so remember this guy up here, which implies B epsilon delta y of y. Now you just translate everything, remembering that y is equal to t of x, b delta x of x, and b delta x of x, that thing was in u, that's why I underlined it right now in red. This is in t of u, right? And that's what you wanted, right? So now you have shown that indeed there's an open ball sitting in the image of the open set, so T is indeed an open map. So T is open, T of U is open, and the proof completed. Okay, so that is it. So this took a while. The initial step, that was the important one, that the bare category theorem asserts existence of this one member there, T b sub n 0 of x, unfortunately only in closure, that has non-empty interior. And then everything that came afterwards was an argument to remove essentially that closure on top and still have the same statement at the end. Okay. This is good now. Now we have proven this, and now the next thing will be another big theorem, that is the inverse mapping theorem. And then there's a few other smaller theorems, then another big one, and then we will be done with this section. I'll see you soon.